Hi there, I'm Nix, and the topic of today's video is solving the remove nth node from end of list problem on the LeetCode website. As always, I'll give you all the details of the process, through the planning of the algorithm, to the coding of it, to the analysis of time and space complexities, as well as looking at LeetCode rankings. If that sounds interesting to you, then stay tuned. Welcome back, and let's get started. We're given the head of a linked list, and we want to remove the nth node from the end of the list and return its head. So we are given example 1 here, a very simple 5-member list, and n is equal to 2. Now note, when it says nth node from the end is this null signal that exists at the very end of that list. It's not the last value in the list. So in this case, with this end being the null signal after the last value, first from the end would be the 5, second from the end would be the 4. So we need to remove the 4 node and have our list go from 1, 2, 3, 4, 5 to 1, 2, 3, 5. We have further examples to drive home the point, and some basic constraints restricting the values and the amount of nodes that can be in the list. Finally, an interesting follow-up question: can you do this in just one pass? Which is what we're going to do. So with all of that information, how do we solve this? Well, the only thing that we're going to be given is the head and the n integer. Knowing that n integer means we know how many places from the null signal we need to be, but we don't know how big the list is and how many places we need to go through in order to get to the node that we want to remove from the beginning. However, by using multiple pointers, we can have one pointer get a head start going through the list that's equal to n. After it has moved n places, then we start moving both that pointer and another one the same number of steps, 1 step each, until that pointer that had the head start reaches the end. And when it reaches the end, the slower pointer will be pointing exactly where we want it to be on the node we need to remove, because the number of spaces between that slow pointer and the fast pointer is the same as the distance between the null signal at the end and the node to remove. And of course, once we're there, we can perform the pointer switches to reroute 3's next pointer to point to 5 instead of 4, and then free up node 4 to delete in this example. Now, that's all wondrous and amazing, but consider the example of what if we had this same list, but n was 5 instead of 2. So when we advance our pointer that gets the head start, it advances all the way to that null pointer, whereas our slow pointer hasn't moved yet. If we go through that initial loop to give the fast pointer a head start, and if that ends up all the way at the end of the list, then we know the node to remove is going to be the head. And that is a sort of special edge case that we need to take into account. Because we can't simply delete the head. We need to make the new node, the one after it, the new head and return that. Plus, the head doesn't have a previous node that we need to reroute to point to the next one after it. So it is a little bit of a special case that we need to take into account first. So to sum up, here are the major points that we need to tackle for our code. First thing we need to do is create some pointers. We need at least 2, but I'm going to make 3. We need a fast pointer, the one that gets the head start. We need a slow pointer, and I'm also going to create a third pointer that I can use to store the previous node, the one right before the node that we need to delete. So first step, make some pointers. Next step is a for loop that's going to go n times and advance that fast pointer n steps ahead in the list. Once we have that step done, then we can check to see if that fast pointer is already equal to null. If that's the case, we know we need to remove the head, and we can delete that node, make the next node in line the new head, and simply return that new head. If that fast pointer is not equal to null yet, well, we need to get it to equal to null. It needs to get to the end so that our slow pointer can advance to equal the node that we want to remove. So that loop will finish off any further steps we need to go and advance both the fast pointer and the slow pointer one step each. Next thing to do is, after we've gotten to the correct point, we need to do some rerouting of the next pointers and then go ahead and delete off our node. After all that is accomplished, we return the head and we are done. That's the plan, so let's get to coding it. Here are the 3 pointers I'm going to use. The first one, list node pointer, I call list end. This is my fast pointer that is going to be used to get to the head start, and this is the one that's going to go until, as its name suggests, it reaches the list's end. And I've set that initially to equal the head. The next pointer I have is aptly named node to remove, and this is also initially pointing at the head. And then I have a third one here that I name node before removal, which I have yet to assign to anything yet. Next up, we need to give list end its head start. We do this via a for loop, and we want to go from I equals 0 to I is less than n, and increment every time. And as long as list end is not equal to null, we just advance it one space. So list end is equal to whatever its next pointer is pointing to. Next up is handling the special case of deleting the head. After this for loop, if our list end pointer is equal to null, it's gone the entire length of the list and we need to remove the head. But in order to do that, we need to reassign what the new head is. And to do that, you can do head is equal to node to remove next. And in this case, node to remove is still equal to the head. So you can have it like this. You could also say head is equal to head next. Both of them are going to accomplish the same thing. Next up, we want to delete node to remove, free up that memory and clean it up well, and then finally we return that newly reassigned head. Now that we've taken care of this special edge case, we can continue on with getting our pointers into the correct position. So if we aren't yet at the list end, well, we need to advance however many spaces it'll take for us to get there. Since we don't know how many steps that is going to take, that's perfect use for a while loop. So while list end is not equal to null, we need to do a couple of things. First thing I do is I want to assign node before removal to equal whatever node to remove is currently set to. After I have that recorded, then I want to advance list n to whatever list n next is, and then I advance node to remove next. So list n moves 1, node to remove moves 1, and I have the previous node to remove recorded in node before removal. After this while loop completes, we're going to be exactly where we need to be. Node to remove is going to be exactly on the node to remove. The node before removal is going to be the node right before it, and the list end is going to be at the list ends. So they all earn their names after this loop occurs. That now frees us up to do the rerouting of the next pointers. So we want to assign the node before removal's next pointer to bypass the node we need to remove and point to the node to remove's next pointer. In other words, we don't want this 3 node pointing to 4 because we want to remove it. We need 3 to point to 5. Now that we have that done, we can simply delete node to remove, again, freeing up that memory. And then finally, after all is said and done, the only thing left to do is return the head, and we are done. Now for this problem, I don't think doing these deletions are strictly necessary in order for the website to accept your answer, but there's no way I'm going to leave empty nodes to muck up, and you would never leave those in code to begin with, so that just opens you up for memory issues down the line. So you always want to free up that memory and call delete when you want to remove something. While it's probably not strictly necessary for it to pass this problem, it's just something you would need to do anyway, so that's why it's in there. Now is the time for clicking buttons and seeing if I have messed anything up. And so far I get lovely green text. That's good. Let's do a custom test case. And instead of 2, be 5, so we're removing the head of 1. And let's see if it can handle that as well. Judging, more judging, finished. Excellent. It has successfully been able to remove the head with no issues. So let's go the full shebang and click the nice blue button and hopefully get nice green text. Last bits to do before we click the details button and see our rankings is to analyze time and space complexity. For space complexity, all I have here is these pointer variables, which take up constant space. So this would be akin to big O of 1 space complexity. For time complexity here, we have to pay attention to these loops. And the combination of these two loops here are going to go through the list exactly once. Thus, the amount of iterations depends on how big the list size is, which we will call n. So the time complexity of this code is going to be big O of n, which is pretty good. And note, we have indeed accomplished this follow-up question, doing it in only one pass. And although I have multiple loops here, this for loop serves to give the list end a head start, and if we aren't already at the end, this while loop serves to get us the rest of the way there. So we're only going through the list once. Now let's go ahead and see what the rankings are. Okay. We are on a little bit of a low ranking. I have seen it ping pong around here, so take the rankings with a grain of salt. And memory beats 96.89. Cool, but again, I've seen it ping pong around to here, as well as not even being on lists, being like 10.8 or something. So again, it ping pongs, and again, take it with a grain of salt. But with that was how to solve the remove nth node from end of list. I hope this video helped you out. If it did, consider subscribing. And as always, I will wish you happy coding and to have a nice day.